Alright, good day guys. Welcome to this video. In this video, we'll be looking at a quick revision on the concept of the chemical kinetics, order of reactions, Arrhenius equation. Perhaps while going through the last year past question, saw some question under this concept. Now, most students will forget the formulas under the chemical kinetics before exam. So in this video, we'll be looking at basically the key point. And some things to know, which are the formulas and how they set the question last year. So now basically, let's start with something under this chemical kinetics there. Now, first thing first, chemical kinetics is dealing with the rate of reaction, the rate at which a reaction occurs. Now, we have the rate of reaction denoted by R equals the change in the concentration of a reactant, or let's say a product, with respect to time. So it's just more like rate of change of reactant or product with respect to time. So the concept lies in between the fact that for a reaction to occur, the reactant must be used up while the product is forming. So just saying the rate at which the reactant is disappearing is also the rate at which the product is going to be forming. So now from this point here, we have that mathematically rate, if we can remember, equals change in what there? Rate equals change in conc, that's the concentration, over the time. Like, let's say the change in time. This is data for denoting change in time. So quickly, now this is just the mathematical expression for what rate of reaction is. Now, if we have that a reactant A plus B forms C, that is, a reactant A reacted with B to form C. Now, how do we write the rate of change, or rate at which this A is disappearing and this B is also disappearing to form the C? Now, we will now have that, using this concept, we will now have that the rate at which A is disappearing is going to be something of dA. Now, when we do something like this, when you put something like this, which is squared bracket A, it means concentration. Now, if you say squared bracket B, it means concentration of B. So the concentration of B dt, because we can relate differentiation to rate of change. To rate of change. So now, because it is disappearing, hence we have to put negative here. So this video is just to remind us of some key point there. So because it is disappearing, we have to put what? Negative sign here. So it's just what? Rate of disappearing of this reactant A. So it's also equal to this rate of disappearing of reactant A is also equal to the rate at which this B is also disappearing. So you can just say minus the concentration of B over what there? Over the T. So this is also saying the rate at which the B is disappearing. So now from here, we can also equate it to the rate at which this C, which is the product, is forming. So the rate at which this product is forming there, it is the concentration of C over the T. So this, we are not putting the negative sign or the minus sign, because product is forming or product is appearing while these are disappearing. So this is just to remind us of how to go about it. In questions, they could give you the concentration of B and ask you to get the rate at which C is appearing. So those are the kind of questions that could be set around this man here. Now, next up, let's talk about something else. Let's talk about the rate laws. Let's talk about the rate law. Now, in this rate of reaction, when we have reactant A, let's say we have reactant A forming C. Let's say we have reactant A forming C. Now, we'll use this concept to talk about order of reaction there. Order of reaction. Now, when we have reactant A forming C, it is known that the rate or order of reaction is just telling us the dependency of the rate of reaction over the concentration. So first thing first, when we have rate equals something of K. K is known as the reaction constant or rate constant. So we can say A, it's always depending on the reactant. You understand? The rate of reaction depends on the reactant. Hence, we can say this one here, or let's just say A plus B. So the other reactant is B there. And perhaps we can say this is raised to power M, right? And this is raised to power N. So this is just what they are raised to power is called the order of reaction. Now, to get the total order of reaction for this particular reaction is now going to be what? It's going to be M plus N. Note that. So whenever they give you a reaction, a rate of reaction relating to the reactant, and they give you some numbers or some values acting as a power for this concentration, so you just have to add up the numbers for you to get the total order of the reaction. It's part of the past question. Now let's quickly remind us of some formulas to note under the zero order of reaction, first order of reaction, and the second order of reaction. Now for the zero order of reaction, first order and second order, I'm just going to be giving us a brief formulas and important formulas. So it's going to be like because we have two kinds of formula there. We have the differential one. We have the formula in the differential form, like in form of this, and we have in the integrated form. Both are very important, but mostly they do ask question under the integrated form. So now, basically for the zero order, the differential form, let me just say the differential form is R, right, equals K. That's just it. So, and you know that R is the rate of reaction, so we can also rewrite it as let's say minus dA dt equals K. Why am I putting minus? Because I already told you that it's depending on the reactant. When you see rate of reaction, they are depending on the reactant. So this man here is also rate. That's why they say zero order of reaction. That's why it is called zero. Zero order of reaction means the rate of reaction does not depend on the concentration of the reactant. It's only depending on the rate constant. So that's just it. Another question they could ask from here is, what's the unit for rate constant in zero order of reaction? Now you should know that rate of reaction on its own equals, since we have here that it is equal to change in concentration over time, that is, concentration as formula, the unit for concentration is molar, or let's say mole per dm cube or mole per liter, and the unit for time is second. So we can say this one is what? Mole per second. Or perhaps we say, since 1 molar equals 1 mole per dm cube there, or 1 mole per liter. You can just say this is what? Mole, let's say per liter, mole per liter, per second. This is just how we can write it. So this is the unit for the what's it called there? The unit for the rate constant when we are talking of the zero order. And we are talking about the differentiated form. Now to the integrated form. Let's say the integrated form. So the integrated form, the formula there is that we have to know that what do we have here? The concentration of that, this is it, equals something of this nature. You see, when I'm putting squared bracket, it simply means the concentration minus KT. So this is the integrated form that we have to know. This is just the final concentration. This is the initial concentration. That's why it is not. This T means after this time, the concentration that is remaining. And the K is the rate constant, as we all know. So this is the formula for it. And perhaps if you want to rewrite this, you can say AT equals minus KT, right, plus A naught. So you can just relate it to equation of line. This is what that's mx bar plus c. So now you can, from here you can see this is your intercept, because they might ask question on which is the intercept when this man here is plotted against time. So and your slope is always negative, like negative k. So that's basic thing to know under this zero order. And know that zero order does not depend on the concentration of the reactants. Now let's look at the first order. If you look at the first order here, now first thing first, let's look at the differential form. The differential form is that R equals what? Ka. So you can see here that it's depending on the rate is depending on the concentration, but it is raised to power 1. That's why it is first order. So this is just what we have to know there. Now let us get the unit for this K. Now it's very important, because they might ask what's the unit for the K constant in this thing. So we already know that this man here, it is what? Rate, that will be R. If you make K subject from, that will be R over concentration of the reactant. Now this man here, it is M, right? Because it's molar per second, and we know that concentration is simply molar. So molar cancel molar, hence we have what? Per second. Hence the decay, what is it called? The rate constant for first order, the unit is what? Per second. Now there's the integrated form. We have to know this formula. So now the integrated form is that this is it. So we have ln of the final concentration. So we have ln of the final concentration equals the minus KT, just know the formula, then plus ln of the what? Initial concentration. So this is what we have to know here. So you can relate it to what is it called also? You will still have negative slope when we are talking of the first order. It's only second order that we have positive slope there. So that's just it. To have a straight line, we must have a negative slope for the first order also. So this is the integrated form, and this means this is the final concentration of that reactant, initial concentration. So this is the time period for the maybe decomposition or something like that. That's how most questions come from this angle. Now let's look at the second order. Let's look at the second order. Now the second order is simply, so the differentiated form is just R equals K. So instead of A raised to power 1, it will be what? A raised to power 2. So that's just it. Now let's try to get our unit for K. K will be R over A squared. I already know that K is molar per second and A is molar. So squared will be molar squared. that will be 1 cancel 1 here, so we'll be having like m raised power minus 1 then per second. So this is the unit for the rate constant when it comes to second order. Now for the integrated form, we simply have that it is 1 over the final concentration of the reactant equals Kt. It's only this one that does not have minus. The slope is simply plus. So plus what there? 1 over the initial concentration. So this is what we have here. So that's all we need to know basically that will help us in solving when we are given any problem under this particular thing. So before we end this video, let's quickly brief their half-lives. Now for the zero order, the half-life is given as, that is the time taken for half of the concentration of the reactant to decompose. So equals what? It is equal to, now the half-life is equal to concentration of that is the initial concentration over what? 2K. So just know this formula, that the half-life depends on concentration. It's very important, and this is their relationship. Now for the first order, the half-life formula is more like the radioactive formula, because there is a relationship between first order reaction and radioactive. Is a kind of radioactive, so they can ask radioactive decay is a kind of what order of reaction, is a kind of first order, because the half-life from here you can even see it is what? Ln 2 over what there? Over K, and it is 0.693 over K. You remember when you are doing the concept of radioactivity, this is the formula for the half-life. So radioactive decay is a kind of half-life, is a kind of first order reaction. Now to the third one, which is the second order. And the second order, so here what can we point out? We can point out that the half-life for first order does not depend on the concentration of the reactants, but the zero order depends on the concentration of the reactants. Now the half-life for let's also see whether this one depends on, so it is what? 1 over K. It is 1 over K then A naught. So this one, the half-life of zero order is directly proportional to the concentration of the initial concentration of the reactant, but for this man here, it is depending on the concentration of the reactant, but their relationship is inverse. Just saying for the second order. So for the second order, their relationship is inverse. Just saying half-life equals 1 over A naught. When we make K constant, like K, we ignore K. This is just it. So their relationship is just like inversely related. But this one, so these are the key things we should note. So let's look at another thing called the Arrhenius equation. Now when we are talking of the Arrhenius equation, so basically we've been talking about the first order, second order, and revision about it. Now let's quickly revise on Arrhenius equation. We just have to know the formula, no calculation on it. We can use the formula to calculate, but no, from the PQ I've not seen any calculation on Arrhenius equation, but there are some theoretical question that has been asked on this concept. So now by mathematically, Arrhenius equation is just relating rate constant, which is K, with the Arrhenius constant, which is A, with the activation energy. So with the activation energy, which is EA. So now the formula is given by K equals A, which is the Arrhenius constant, then exponential EA over RT. So the exponential is what? Minus EA over RT. So this is the formula to know. Maybe for calculation, the R is the gas constant. Our gas constant that we know is 0.0021 stuff. So this is the temperature in Kelvin. So now there is actually a question in the past question that is asking about the logarithmic form of this Arrhenius equation. Now the logarithmic form of Arrhenius equation briefly is given by ln k equals minus EA over RT, and that's plus ln A. Now this is the logarithmic form. Now I want us to do something here. Let's relate it to equation of line. Now for us to have a straight line, we have to relate it to y equals mx plus c. So there's actually a question that that's asking about when this ln k is plotted against 1 over t. You understand? It's plotted against 1 over t. What will be the intercept under the... Now when ln k is plotted against 1 over t, like what will be the intercept or the slope? So that's the question there. Now let's look at this logarithmic equation. From here now, let's say our ln k, let's also rearrange this man here. Okay, we've rearranged it. We have something like this. Now for m, is plotted against 1 over t. From this man here, we can say minus EA over R, right? Then multiply by 1 over t plus ln A. So from here now, we can say that this is our y, this is our m, which is the slope. So this thing, please know it, the slope is EA. The slope is the activation energy. This thing is constant, so we don't really need to put more emphasis on it. So the slope is activation energy. The x-axis is 1 over t. So this is the x-axis, and the intercept, which is very important, please take note, is what? Ln A. So there is actually a theoretical question on this. So that's all about the revision under the chemical kinetics, order of reaction, and the Arrhenius equation. In the next video, we'll be looking at the past questions on each of these concepts.